topics today. One is independent events, and the other is going to be Bayes' theorem. Bayes' theorem is one of my favorites. Independent events, the outcome of one does not influence the outcome of the other. So, in other words, I like to think of it this way. Let's say you draw a card out of a deck. Okay. If the first one isn't going to influence the next one, what do you do with that card? You got to put it back. So this is what I call the put it back effect. You put the thing back. One does not influence the other. Does rain influence? Rain doesn't influence shine. This is a little, I think that may not be totally true, but if it rains today, does that affect whether it's going to rain tomorrow? Sometimes, but it really doesn't that much. It could still rain or shine tomorrow. If we do drawings like ping pong balls of different colors, and you draw a red sphere, okay, and there's red and white ones, if you draw that, if you put it back, then it's going to have the same result. What we're talking about as far as conditional probability is that in conditional probability, if the probability of A then B is the intersection of A and B over probability of B, we're good. Only if that intersection is the product of these two. In other words, you put it back, it's not conditionally effective of one to the next. Did that string thing I did where you tied the string, after I tied the bottom, the three on the top and I tied the first one, did that affect the others? Yeah, it did. So that would not be independent. But if I untied them each time and then tied them, would it be independent? Yeah. So the way mathematically of looking at it is that when the probability of A intersect B equals P of A times P of B, look what happens in the conditional. Probability of A times probability of B over probability of B. What is it? What is this equal to? Probability of A. So when the conditional, what happens is that you still can figure out the intersection of the two. There's still an intersection. This is not mutually exclusive. That's not what we're talking about. We're talking about when they do intersect. What's happening is that you can predict that that probability of A doesn't change when you look at the second time. Okay? So I like that. It's just a little confusing, I think. And then we get to Bayes' theorem. This looks so complicated, doesn't it? Doesn't it look complicated? It looks awful. Let me walk you through it, and then I'm going to show you the easy way to think about it. Bayes' theorem is saying that there's two things that can happen, A and B, but there's also a not B. So when you look at A, it can exist in two worlds, the B world and the not B world. So when we look at the probability of A, what we're looking at is where B union B intersects A. That makes sense, doesn't it? Because you're going to get a little bit of B and you're going to get a little bit of B not. So you're going to have A intersect B, which is this part. Correct? That's this. And then you're also going to have, ooh, that didn't show up. How about green? You're also going to have A intersect not B, which is this part. Okay? So the probability of A is equal to the probability of A intersect B union the probability of A intersect not B. So we just did a probability of each of those. Are we okay so far? So now I'm going to do a little bit of going back in time here. What was the probability of A knowing B? That was the probability of A what B? Intersect B over the probability of B. And then this one is the probability of A intersect not B over the probability of not B. We're going to cross multiply and solve for probability of A intersect B. I'm going to solve for this, and I'm going to get the probability of A intersect B is probability of A knowing B times the probability of B, just like our last problem that we did, the babies. And then we do the probability of A intersect not B is probability of A knowing not B times the probability of not B. So then these are substituted in here and here. And so that gives me this new probability of A is this plus that. Is that clear as mud? Yeah, clear as mud. But I did prove it. I did show you how it came to be, but that's not how we're going to do this. This is Bayes' theorem. This is Bayes' theorem. And Bayes' theorem is the probability of A knowing B. It's going to be this thing. And then for probability of B, it's going to be this mess. But we're going to look at this a little bit differently. We're going to use this tree diagram to help establish our probabilities. And we're not even going to use the formula. I'm going to use the idea that there's two things that can happen, either A and not A. And then if A happens, we'll have this conditional. If A doesn't happen, or if A happens and B doesn't happen, you get this one. And likewise, you're going to have the same thing here. If we have B, and then this is going to be my not B. An example is going to make this all easy to understand. These will be your favorite. And what's great about these is on IB tests, they have these wordy problems. Most people look at them and get frightened, but you won't. They'll totally make sense. Yeah. I'm going to show you. Okay. So let's say we have two machines, and what you're using this idea of defective and non-defective. And a lot of times you're going to have two situations, and they're each going to have defectiveness qualities. So we're going to look at probabilities knowing those. So let's take an easy one. This one's really easy. You have machine A or machine B, and you're going to make something at some kind of shop, and you're going to 40% chance you're going to use machine A, 60% chance you're going to use machine B. Okay? Both of them can be defective or non-defective. Let's say machine A has a defective probability of 0.3. A non-defective probability of what would that be? I'm sorry, 0.03, not 0.3. This would be 0.97, right? And then this one, machine B, if you happen to use machine B, it's 60% chance, but that one has a 0.05 defectiveness, and this one has a 0.95 of being just fine. So have you figured out what I'm going to ask yet? What's the chance of something coming out defective? Okay, or not defective. An item selected is defective. What's the probability that it's machine B? Okay, so I'm going to use the highlighter here. I'm picking something that's defective. Which arms are these? Well, I call them arms. I'm going to go here, here, but there's another arm that I could use here and then going up there. So let's look at these arms. This is the probability that we're defective knowing it comes from machine B. Okay? So what I want to know is what's the probability that it's defective and it's coming from machine B. Which arm is it? Is it the, I'm going to try something here. Get a little bit different colors. Use a blue here. Blue. Come on, blue. There. Yeah. Looks the same. Yellow's not going to work any better. Can I do purple? There you go. This is 0.05. Okay, so which of these is going to be defective and machine B? The green arm or the red arm? The red one. And then for the bottom, we're going to have the probability that it's defective and machine A, and it's defective and machine B. So all that's happening here is that we have this wonderful intersection, but it's intersecting twice, and we're picking a certain one. We're picking the B defective one. So this B defective one is just going to be 0.6 times 0.05 over the sum of these, 0.6 times 0.05 plus 0.4 times 0.03. We're not looking at all of the things. We're just looking at the defectives. That's that conditional. You can think of Bayes' theorem as being a conditional total again. And then we're looking at the intersection of the first and what we want. So tell me what this is. I think it's going to be 0.3 over 0.3 plus 0.12. Or 0.3 over 0.42. Does that sound right? Am I missing zeros? But I multiplied this times, oh, there is another zero in there, yeah. Thank you. And then 0.0422. Okay. Thank you. And then what do you get? 0.74. A 74% chance that if it's defective, it came from B. So which would you rather it came from? A, because it's going to be 26%. But isn't it interesting how just the little bit there made such a big difference? Not super. And we could do this, let's say that we had an item came up and it was not defective. Okay, what's the probability it came from machine B? Okay, so all I'm going to do is it's not defective. Okay, now the arms are going to be a little different. Diogo, do you see how we use this? It's kind of cool, isn't it? Well, I've got an even better example coming up. All right, so now we're going to look at not defective. So the first one is going to come from not defective there. The second one is going to go not defective here. So when we figure these out, I'm going to get the probability that it came from B and it wasn't defective is going to be 0.6 times 0.095. And then you have 0.6 times 0.095 coming up again. And then we're going to have 0.4 times 0.97. And what do you get for that one? Hey, how are you doing? If you get your calculator out, try it. What do you get for this one? 0.59. So you have a 60% chance that it's not going to be defective. If or a 60% chance it came from B if it wasn't defective. So it's kind of, wonder which one we want to pick. For the homework, I have a number of problems for you to solve. This one I don't think you'll have trouble with, and this one is good. I love these problems. Would you go to this number 9? This is the one we're going to start with. I'm going to stop the video, but start with this number 9. This is incredible.